Hi everybody, so today we're going to finish up chapter 11. So we're looking at the chi-square distribution. We looked in the previous sections at what is a chi-square distribution, what does it look like, what are some properties of it, and then in the last section we looked at how to use it to compute a goodness of fit test, so comparing how distributions look against each other. In this section we're going to look at tests for independence. So the chi-square test for independence is used to determine whether there is an association between a row variable and column variable in a contingency table constructed from sample data. The null hypothesis is that the variables are not associated, in other words, they are independent, and the alternative hypothesis is that they are associated or dependent. So again, the null hypothesis is that the variables are independent, okay, so that they have no connection whatsoever. The alternative hypothesis is that they are associated in some way. Okay, so we're trying to show whether or not they are dependent on each other. Okay, so the idea behind these claims is to compare actual counts to the counts we would expect if the null hypothesis were true. Okay, so if the variables were actually independent, what would we expect to happen versus what do we actually see happening? Okay, and if what we see happening matches up with what we would expect if they're independent, then we just say, yeah, then they're probably independent. But if we go under the assumption, well, this is what I would expect to see if they were independent, but this is what I actually got, and that's pretty different, then that would indicate that we do have a dependence there. So recall if two events are independent, then we can compute their probabilities by this formula. So probability of E and F equals the probability of E times the probability of F. If we want to use this to determine our expected frequencies, which is what we're going to talk about right down here, okay, so we can look at the expected counts as being row total times column total over table total. So to find the expected frequencies in a cell when performing a chi-square independence test, multiply the cell's row total by its column total and divide this result by the table total. Okay, so this is one that we need to know because we're going to be working with it. So expected frequency is row total times column total over table total. So, and if that's a little confusing as to what that means, let's look at this example here. So in a poll, 883 males and 893 females were asked, if you could have only one of the following, which would you pick, money, health, or love? Their responses are presented in the table below. Determine the expected counts within each cell, assuming that gender and response are independent. Okay, so let's go through a couple of these together and then I'll just show you guys the rest. But when we're talking about row total, column total, and table total, so the row total is just the sum of all of the terms across a row, which this table also gives to us, so that's this value over here. The column total is just going down the column, okay, so that's this value down here. And then the table total, this one also gives to us, this is just the sum of all the values in the entire table. So those give us that 1776 down here. Okay, so we take those values, do the appropriate multiplication and division, and then that's going to give us the values we need. So for our first expected value, so let's look at this one right here. Okay, so this one represents the overlap between money and men. Okay, so for this one, to get the expected count, so expected value, expected frequency, whatever you want to call it, this is going to be row total, which is 883, times column total, which is 128, over table total, which is 1776. Run these numbers through a calculator or through Desmos, whatever. You will need technology to be able to do this because these numbers are pretty messy. And you will get approximately 63.64. So that means the expected frequency in this first cell is 63.64. Actually, let me go ahead and just type that in. That'll be a little easier to read. So that gives us 63.64 right there. Okay, and then if we want to move on to the next cell, we can just move to the right. So if we're talking about the health column now, so now we're in this column. So we're looking at this term right here. Okay, so that cell, so the expected value, what we would expect to get if these were independent, we would expect row total, 883, times column total, in this case is 1020, over table total, which is still 1776, which would give us approximately 507.13. Okay. And we would just keep doing this for each element in this table. Okay, so you do it for all 6, and then you're filling in this new table here with all these new expected counts. Okay, so let's see what this gives us here. So let me just move this over. So we said this one gives us 507.13. And then love, if you compute that expected count, you get 176.50. Now if we move down to the second row, so again the new row total is 893 for women, times the column total over the table total. Okay, so those values are all getting drawn from the same pool here. But this one we would get 23.13. The next one we would get 512.87. And the last one here we would get 315.77. Right. So these would be our expected counts for this table. Okay. So now this leads us into how we conduct our hypothesis test, okay, our test for independence. So let's look at the next page. So there's not going to be too much different from what we've done already. So the steps are very similar to what we've seen. So determine the hypotheses, determine your significance level, calculate those expected frequencies. Okay, and again, that utilizes this formula, so we add them all up. That gives us our test statistic. Okay, so remember again, this is observed value minus expected value squared over expected value. Okay, so we can use that formula and of course incorporate the technology to help us as well. Okay, and then p-value approach, we're going to do the same thing we did last time, which is we're going to use the classical approach for this. Okay, so with appropriate technology you could certainly use the p-value approach, but we're just going to use classical for this one. Okay, and then of course make our conclusion at the very end of the problem. Okay. So let's take a look at the example. So this is the same question. So we have the poll with 883 males, 893 females. If you could only have which of the following, which would you pick? Money, health, or love? Their responses and expected values are present in the below tables. So this is the expected values that we found on the other page. And then, of course, the original table there. Test the claim that gender and response are independent at the alpha equals 0.05 level of significance. Okay, so our null hypothesis is always going to be that they are independent, that there's no relation between the two. Okay, and then the alternative is that there is some relation. Okay, they are dependent. Okay. So now we are going to need to create our test statistic. Okay, so this is going to be right there. So our test statistic, so chi-squared not. So this is observed minus expected, right? So it's observed minus expected squared over expected, and then add up all of those terms. So let's go ahead and do that. Okay, I'm just going to show you a few, but then we would just obviously keep going with the process. So first cell, that's this one. There's our corresponding expected value over here. So we have observed minus expected. Okay, and I'm going to use the numbers we found. I rounded one extra decimal place, so it just makes it even that much more accurate, over expected. Okay, plus, next one, observed minus expected. Again, I'm using the one that we got with 2 decimal places. So squared over expected. Okay, and then plus, and we add up all the way. So we do this one and this one and this one until we get to that very last one. So we get observed 273 minus expected is 315.77 squared. And if you use the values they gave you in the table, that's fine too. I'm just going based off of what we found earlier. 315.77. All these terms added up together give us approximately 228.88. Okay. So that's our test statistic. Now, what does this tell us? Well, using the classical approach, we need to determine what our critical value is. Okay, so we have our chi-square graph here. There's going to be some value that is chi-squared sub alpha, and we need to determine if the test statistic lies inside this critical region or outside of it. If it lies inside, that means that we do get to reject the null. If it lies inside, we're not able to reject the null. We say there's not strong enough evidence. Okay, so in order to get that critical value, so chi-squared sub alpha, which in this case is 0.05, we need to go back and use that table. In order to use the table, we need to have degrees of freedom. In these types of problems, the test for independence, so you'll need to know this. It doesn't say it anywhere on the text, but we need to know the rows and columns. So we have 2 rows and 3 columns. So the degrees of freedom are going to be number of rows minus 1 times number of columns minus 1, which is 1 times 2, which is 2. Okay, so it's number of rows minus 1 times number of columns minus 1. And that's going to give us our degrees of freedom, which in this case is 2. So if we go back to that table with the degrees of freedom and with our corresponding alpha value here, we can go ahead and get that this value would be 5.991. Okay, so now we're comparing this value, okay, our critical value with our test statistic. And we look and we see that clearly our test statistic is vastly outnumbering our critical value, right? Critical value is at around almost 6. Our test statistic is at 200 something, so that's way out there. Okay, so this tells us that we are able to reject the null hypothesis. So if we're rejecting the null hypothesis, what does that mean? Well, the null hypothesis, the status quo statement, said that there was no relationship between gender and response to this question. But we have significant evidence to suggest that that's not true, that there is in fact a relationship, right, a dependency between gender and the way that someone answered this question. Okay. So, let's go ahead and just state that here. So we can say there is sufficient evidence to conclude that gender and response are dependent. All right. And that gives us the answer to our question. Okay, so that's our